All right, hello everyone. So we have our first tutorial webinar on programming interfaces, and we are planning to have more of them. And the idea is to learn about type of methods that are being developed and computer infrastructure for them, and facilitate developing of new method and make the introduction of people to programming smoother, to programming in our group. So what is planned for today? Is two parts. I will first give a bird's view of output cluster and equation of motion calculations and discuss some challenges. And then Evgeny will focus on specific tools that were developed to address these challenges. And we will also look at the specific code and go over this example in order to understand how one should go about adding a new method to CCMAN 2. So we go to next page. All right. Okay. So very brief overview. We are working mostly with output cluster and equation of motion methods, and we can start looking at equations in a very basic form. The ansatz for output cluster calculation is shown here. We have exponential ansatz, where T is an excitation operator and phi 0 is a single stator determinant. That's our reference. In equation of motion, in addition to this ansatz, we add excitation operator R, linear operator that acts on output cluster wave function. So what are the excitation operators? They may have different form. T1 and T2 are shown here. They're plain excitation operator in the sense that number of creation and annihilation operators are similar. And they're linear combination of all possible excitations. And these numbers, T IA, Tijab, they are amplitude of the wave function. So when we solve output cluster equations, we solve for the amplitudes. This is our wave function. So what sort of equations do we solve? In a very general form, we can think about these equations as solving some sort of non-Hermitian eigenproblem. For example, we can formulate our theory using so-called similarity transformed Hamiltonian shown here, where T is this excitation operator. And then for output cluster equations, for reference equations, we can formulate the equations requesting that the projections of this Hamiltonian on the excited determinants are zero. So this would give rise to nonlinear equations for these amplitudes T. For equation of motion, we solve when amplitudes T are already known, we solve for eigenstates, their energies and amplitudes are, and the type of problem that we solve is an eigenproblem. It's an eigenproblem, so it's linear, but it uses this non-Hermitian object, and it's a large eigenproblem, so even though it's a linear problem, we do not solve it by just diagonalizing the Hamiltonian, we solve it iteratively. So the output of this would be energies and amplitudes R, and then depending on what we want to do next, we may want to go for properties and gradients that would require so-called density matrices that are constructed from amplitudes, and there are different ways to do it depending on type of theory we use. So it may also involve solving additional equations, so-called response equations, when additional set of amplitude type quantities will be determined. So this is kind of very rough very simple introduction for people who are not very familiar with that. So what is important to appreciate, which you can easily see by just trying to read chapter 5 and 6 in Q-Chem manual is that we have huge variety of different methods based on cowpot cluster theory. For example, for so-called ground state cowpot cluster methods, we have cowpot cluster doubles or cowpot clusters with single doubles, or Bruckner cowpot cluster, or optimized orbital cowpot cluster, and that's not the full list. Then, as you well know, corrections that include the effect of higher order excitations. In most practical calculations, these are triples, but you can go higher, can be included, and we have several types of them. A simple plain parenthesis T or different twists on the seam. Then we have quite a big family of equation of motion methods that are implemented for excitation energy, for spin flipping type of excitations, for electron attachment, IT, DIT, double spin flip, and this list is growing. Then one can also try to correct these methods by including higher order excitation through perturbations, so similar to reference state calculations and so on. In parallel that, we have also CI-based methods. They are less commonly used. They are similar to equation of motion, but they do not involve cowpot cluster calculation. So we have a bunch of these. Now, what is important that all these methods, for example, when we do equation of motion, usually it means that we need to solve ground state cowpot cluster equation. But what is important is that not all combinations are possible, and there are all kinds of combinations that are not allowed. So if you cannot combine everything with everything, and that there are a lot of parameters that control execution flow and data flow in these calculations. Now, the first 2 points here refer to ground state or reference state and EOM calculations, but energies mostly. If we want to go for properties and gradients, then we need to run additional type of calculations where additional quantities will be computed, and that would be performed depending on what type of methods we used, either after a reference state calculation or equation of motion calculation. There could be interstate properties requested, that yet another type of calculations, and again, these are not available for all the methods. Now, what is also important is that for each particular combination that is legitimate, there could be additional variations that depend either on the chemistry, either on the system, or on specific algorithmic enhancement we want to use, and that would result in a completely different execution and completely different code, and of course will bring additional controls. Examples of this would be like spin unrestricted Hartree-Fock reference or restricted open shell reference, or maybe using non-canonical orbitals from DFT. So this all would bring some differences in algorithms. Another very often used variation would be using Arai or Kolesky representation for integrals for enhanced performance, and this is again is available in some methods, but not all of them, and that has a significant effect on how calculations are performed. Again, it could be completely different code. Things like active space selections, frozen natural orbitals, and so on. Now, what is important here is that there are a lot of dependencies in this, and these different types of calculations are not exactly hierarchical. There is some order in which they should be performed, but what is important is that execution of lower level methods can depend on what we are going to do after that, and I will talk more about it. So what we wanted to focus today is on 2 things. One is how we handle all these parameters that control execution of methods and specific details of calculation, what is the efficient way to do it, and also how do we handle all this multiple data that is produced, data of different type, and what is the efficient way for doing that. So to get ready for that, I wanted to give a brief overview of essential what type of parameters we may have, right? To give you an idea of how one to kind of get ready to discuss how we can organize them. So we can start with something very basic that people see when they just start doing calculation, and which makes a lot of sense. For example, for any calculations in the input, we need to specify what exactly do we want in terms of correlation level, for reference and for target states. For example, like CCSD for reference, equation of motion, CCSD for target states, and so on. Number of target states and their type, can ask for equation of motion, for excitation energies, or for something else, whether we want higher order corrections, whether we want properties, interstate properties, and whether we want to use some of the enhancement. So for each of these options, in addition to just having them available as the input keywords, we need to have some internal parameters that store all this information and based on it set up execution flow. So this is an example of execution flow in CCMAN 2. Again, this is not a general picture. It's just one specific example, and there could be much more complicated diagrams. And I do not think it's possible to write a single diagram that will describe all complexity, not in even 3 dimensions. I think you will need some five-dimensional space to describe all the connections. So most calculation starts with SCF calculations, from which we get Hartree-Fock orbitals and their coefficients. Then usually we perform integral transformation, although it's not required step anymore, because if we do Cholesky decomposition, we don't do integral transformation, we do something else. For many Cowpert cluster calculations, we begin by doing MP2 calculations to get MP2 T2 amplitudes, which we use as a guess for Cowpert cluster. That's very simple calculation, but that's involved. Now, these MP2 calculations would produce T2 as a guess that could be used as a guess for Cowpert cluster. Then in Cowpert cluster module, so to say, one would solve for amplitudes T1 and T2 in CCSD. That would be output of this calculation. Then we have a lot of different options. For example, if we are going to calculate gradients or certain types of triple corrections or certain type of properties, we may solve response equations and solve for so-called lambda, which have a meaning of left eigenvalues of Cowpert cluster problem. Or we may skip this step. Now, what is important is that depending whether we want to get this lambda or not, that may affect convergence thresholds and algorithms in Cowpert cluster routines. So we have not only the dependence that higher level methods depend on what was done previously, but the end goal determines how exactly each specific calculation is performed. So we can calculate these corrections, or we can go and do equation of motion calculations, in which we will solve for energies and amplitudes. Again, after that, depending on what was planned, we can go and solve response equations, solve for L eigenvectors of EOM, solve for T amplitude response, orbital response, and that particular combination will be determined by particular combination of input keywords. Now, another basic type of calculation that could be performed either after equation of motion or maybe after Cowpert cluster calculations directly would be calculations of one particle and two particle density matrices that take amplitudes as input, and then they compute these matrices. And here again, there could be a lot of variety depending on what exact method was used to compute amplitudes and what sort of response matrices we want to calculate. So there are a lot of variety here. Now, bottom line, a lot of data to pass around, and there are dependencies all over. So it's not simple and linear hierarchical chart. Do this first and that first. Now, how this could be handled? So let us now summarize, maybe briefly what sort of parameters and data we may want to handle, and then proceed to practical solutions. So, to summarize what I just tried to explain, a typical cowpot cluster calculations would require several broad sets of parameters. Those that specify what we want to compute, exactly, what type of calculations, then parameters that control algorithms, how, for example, equations are solved. And this may be not so visible for users, but they're very important within actual code. And those, to give you an example, if you request CCSD calculations, you do not need to say anything in input, but within actual cowpot cluster subroutines, you want to know what flavor of GIS procedure you use for solving these equations, how many vectors you use to generate GIS, and so on. Same applies for Davidson procedure, also a lot of things to keep track of and to use to control the algorithms. Then, of course, as I said, we may want to specify flavors of calculations, what sort of reference we used, and whether we used active space and what active space. And this also have effect on algorithm. All right, so what sort of data do we have? As we briefly discussed on this diagram, each type of calculation would require some input data and will produce some output data. For example, CCSD needs integrals and C metrics, and it computes T amplitudes. Equation of motion will need T amplitudes and integrals and maybe lambda, and it will produce right and left vectors. For density matrices, we need all these combinations of amplitudes. For properties calculations, we need to provide density matrices, 1 particle and 2 particle. Now, these are all big objects, and what is also important, they can be of a different type. For example, for density matrices, the formal definition of density matrices looks very simple, but depending on which methods we use to compute wave functions, the actual objects used to compute density matrices can be very different. It could be T1 and T2, or T2 only if we have CCD calculations, or it could be something else. So all what I can say here is that there are a lot of objects, they are large, and we do not want to recalculate them, and we want to store them and make them accessible in some convenient way, and we also want to avoid situation when these objects can be changed by different modules in a predictable way. So we want to be able to control some of this. Now, how it was handled before, and what would be kind of obvious way to deal with that? Well, we used to have this Musgrave type of class called params that would contain all the params. So this is an example of C++ code where we have this class and we have many parameters. So I look today this file, which is just a header file. It has 400 lines, right? So if you want to add new parameter, you add a new parameter to it. So it's kind of ugly, but it's all in there, and you can go and figure out, what is requested, what are thresholds, and so on. How did we manage execution flow? Well, it also wasn't done in a very satisfying way, and this is just a snippet of the old code where you see a lot of if statements, right? Based on, if this is requested, do this, and if that is requested, do that, and then, like passing data from one module to another is also was pretty sophisticated. So this file called CCMAN main, which, kind of a top-level subroutine controlling cowpot cluster codes, has 600 lines, which is not good. So that's not a good style and not convenient and not safe, of course, and it's also very painful to add a new method or to even make sure that it's executed correctly. So today we will talk about new way to manage that and how it's done in CCMAN 2 that uses completely different approach. Now, we already had a lecture on Libtensor, our basic tools used to code equations. Zhenya gave a webinar and it's available on YouTube. Now, Libtensor paper is also out. It describes classes and algorithms, but as you can see in this diagram, it's a relatively small part of all types of different parts of the new code. For example, we can talk about Libtensor, that's obvious, tensor library, right? So it's something facilitates tensor algebra. We have also library of solvers that solve equations using different iterative approaches like DIS, Davidson, and so on. There are top-level routines that control execution of execution flow and output cluster methods, so something like the CCMAN main, but only done better. And there are also different utility libraries, those that help us to deal with, for example, handling information about molecular orbitals. We also have like one library that has a lot of equations coded and so on. So today main focus would be on tools that are used to control parameters and manage data, such that it's done in convenient and relatively safe way, as safe as possible. And also, Zhenya will present an example that will explain how to go about adding a new method to CCMAN 2. What should we do if we want to add a new output cluster, something or other that is not yet implemented? Which parts of the code are most essential to look at after we have our equations coded by using Libtensor? So to set the stage for that, let me just show a couple of slides about CC2 code. Everyone knows what CCD method is. Not CC2, sorry. And here is kind of most basic routine that shows CCD amplitude equations implemented using tensor libraries. So you can see that it's as simple as it gets. So this code is no more complex than actual equations written in the paper. And you see that here, using tensor library tools, you can write it down, all possible contractions, and write down this amplitude update equations easily. So that's, you can learn from tensor library. Then, in order to set up iterative solvers, you need to do certain setup, certain coding to tell the solver library how exactly we want our equations to be solved. We should tell them what is an iterative equations we are solving. We should tell them, when stuff is converged and so on. Now, this is completely different topic, and we probably will have another seminar on this because it's not trivial. But so I will just skip this part today. Let's just know that it exists. And then, here is an example of higher level routine. So this is CCD function that goes through the calculations. And you can see that it's very simple, right? Looks very elegant. So we have here some variables, T2 gas and T2 amplitudes. And we start by importing integrals, making CCD gas, and then, running our solver. So it looks very good, but it immediately raises a lot of questions. Now, where are actually data and how all these solvers and other routines know what to do, where to take stuff, right? So, and that's exactly what would be focus of today's talk. So this is just a picture. So this is a class, CCD, typical class that is written for a method or which has this function which we just seen, and you can see that it takes some arguments here, right? And these arguments of this libctx type, they're coming from libctx, and they have two different types, and so that's so today we will talk about this, and that is the key to figure out how to deal with data and parameters and how to use this tool. So I will stop here, and Zhenya will continue. Maybe we can take a quick look to see if people want to ask some questions.
Okay, so please, if you have any questions, please write it in our questions section, and Anna will be happy to answer them. So let's see if anybody has any questions.
No,
I think nobody is asking. Okay, so now I think Zhenya can continue with his presentation.
All right, thank you. Thank you, Anna, for a great overview of what we're working on. And this talk will focus on how to deal with setting up calculations, passing parameters, and how to manage all the data objects in the couple cluster codes that we have in Q-Chem. And of course, the question is, we have to deal with a lot of different input parameters that come from the input file, and we have to manage all the different types of calculations that have very unclear dependencies. How do we do that so that so that the code that results from this stays manageable, and we don't have crazy files that have to deal with every possible method. So I will start with the parameters part. Yeah, so this talk will consist of two parts. First, I'll discuss the parameters, and then the second part will discuss how to deal with data. And so the new parameter structure is organized as a tree. And a tree is here shown in the picture. These squares are tree nodes, and then each node we assign a name, so it's kind of the label of the node, and it's a string, and then the value. This data structure allows us to create an hierarchical way of representing the parameters. And well, in this particular picture, I have a CCMAN 2, which is the roots of the tree, so a single top-level node. We assign just a value of 1. And then we have two second-level nodes, CCSD and EOMEE-CCSD. The first one has a value of 1, and I'll explain what that actually means in a second. And then EOMEE has a value of 0, and then we can have this whole hierarchy, right? But yeah, so basically this is how tree structures are organized. When we go to the actual implementation of couple cluster codes in Q-Chem, we have Q-Chem read the input file for us. So we don't read the input file directly, but what Q-Chem results in is so Q-Chem reads this user input and produces something that's called a rem vector, where the keywords are translated into just numbers. Yeah, just numbers, and then we can read those numbers, and knowing the formats, we can interpret them as what to do. And so let's look at this inputs on the left. We have let's assume that this is the rem section of the section that sets up the calculation. It's missing a few other parts, like the actual molecule that we're computing. But let's just focus on this. This particular calculation asks for a single point CCSD calculation for the ground state to use 631G basis set, and it also asks for two excited state calculations. One is EOMEE, type calculation, and the other is EOM-IP. And then the number of states is specified by these EOME states and EOM-IP states keys. The value is interpreted as we want 2 states of the first irreducible presentation and then 3 states of the second irreducible presentation. So suppose this is a molecule that has CS symmetry, so we would compute 2 states of the A prime irrep and then 3 states of the A double prime irrep. Then an additional keyword that I put here just for illustration is how we want to change the convergence criterion for the Davidson procedure. So instead of whatever default is, we use 6, which means that the norm of the residual should fall under 10 to the minus 6 in order for EOM to converge. All right, and so inside CCMAN 2, we have an interpreter for these keywords. It's located in the file that calls paramsreader.c. And the code in that file essentially does this. It takes the input file, the rem vector, and produces a parameter structure shown on the right here. So this parameter structure has an actual hierarchical, so it's a tree. It has an hierarchy in it, so we, in this parameter structure, we say that we want a CCSD calculation. This is a direct translation of the input on the left. So we want the CCSD calculation, and then the second line shows that there are some CCSD parameters. I just replace them with a wildcard, but I'll explain what they're. But there's a subtree of parameters for CCSD, and then we have all the different EOM models that we have available in CCMAN 2. We have keys for all of them, except the values are zeros, except ones under the method we actually want to be computed. So we don't want EOM-EA in this calculation. We don't want EOM spin flip in this calculation. We only want EOM-EE, so the value is 1, and EOM-IP, and the value is 1. And then again, this line and this line show that there are some additional parameters. It's just for illustration on the slide. Okay, so now let's look at CCSD parameters. Again, I think these are not all of the possible parameters, but just to show the structure and how these are organized. So we assign the value of 1, which means we want to compute the CCSD calculation. And then inside CCSD, we have multiple modules. One computes T amplitudes, another computes lambda amplitudes. There's another module that computes parenthesis T correction, and so on. In this particular example, we have a T, so we ask for the module to compute the T amplitudes. And then we specify some parameters. The solver, we want to use dice. I'm sorry. Then some parameters of the dice procedure, how we want to work with the subspace, and how many iterations, and what our convergence criteria are. And then again, in this example, we say that we don't want lambda amplitudes, but if we wanted lambda amplitudes, we'd put 1 there and then specify all the parameters for lambda. Now, let me point out a few differences between this and what we had before. Now, this is stored as an associative array. It's not a structure of where each of these parameters is a member of a structure or class. It's not a C++ structure or class. And so if one wanted to add a new parameter, you don't have to change a .h file or modify any class. It's just you add a parameter to this array, to this tree, and then you add it in one place that prepares these parameters, and then read it where you want to actually use it. Right, and then so the second difference, we actually add an hierarchy to these parameters. All right, and so let me go to equation of motion example. It's a little bit bigger. There are more parameters here, but I'll just show you how they're structured. So here we enable EOMEE. We set up that we're going to use an RHF reference. Let's suppose that in the input file we have the molecule, this is closed shell molecule. So we're going to use an RHF reference, and we want singlet excited states. And then we have two reducible representations in our point group symmetry, and we specify a section to solve for R amplitude for each rep separately. And then for the first rep, well, the number here is arbitrary, so here it starts from 1, 1, 2, and so on. But the actual rep numbering in the code starts with 0, so we assign the value of rep as 0, which is the first irreducible representation, A prime. The number of roots is 2, so remember we asked for 2 states in the A prime rep. And then additional parameters is how many guess vectors we want, and what kind of solver. Right now we only have Davidson, but potentially we could have other solvers, and then some convergence criteria. Remember we modified this one, so this convergence criterion is 10 to the minus 6. Right, and so the same idea for the second irreducible representation, except this for the second one we ask for 3 states. And you'll notice that the structure of this R subtree is the same for the first and second rep, which means that we can, by setting up this hierarchy, suppose we have a function or a class that solves for R amplitudes in EOME. What we can do is simply pass to it this subtree that starts with R, and then that class will not even know or care about where it was called from as long as it knows its own parameters. This is an important difference because we want to maintain encapsulation of our in our implementation. So each method should know what it needs as an input data or input parameters. It knows, well, of course, what kind of data it produces, but it should not know about how the results will be used because it shouldn't care about it. It's just its job is to produce the results, and that's it. If we, that eliminates a lot of complexity because, well, if we don't know how the results are used, then we're pretty independent. If we have to know, if you want to know how the results are used, then you need to add all those dependencies, and well, it's just a bad way to do this. So we want to remove as many dependencies as possible. All right. So the main point here is that we can isolate the subtree and pass it independently from the a higher level structure to the routine, and then it will deal with these parameters. Okay, and so the class itself, it's located in libctx. The class is called params, and let me go through this little code snippet. I'll explain to you how it works. Well, the first line we're just saying, I'm just saying that I'm using a standard string class later here, and then okay, so this param structure par, suppose it comes to us from somewhere. We don't know. Maybe a caller passes to us this parameter structure. It's constructed somewhere before. We don't care. So we just have it. All right. And then we started looking at it. So first so this line tries to take out a subtree that's labeled CCSD. So suppose this is a CCSD. This code is in the CCSD procedure, and so we want to know what kind of parameters we have in CCSD. So we extract the CCSD subtree. From the CCSD subtree, we extract T. That will be parameters pertaining to the solver for the T amplitudes in CCSD. And then we want to know what kind of solver. Suppose we have dice and another awesome solver for CCSD. So we want to know what kind of solver we actually want to use. And so we extract this value that's labeled solver as a string and put it in the variable called solver. Now, okay, so let's look at this line closely. T is just an object of class params, and then get is a templated function, and this string in the angle brackets means that we want to extract a value of the type string. This is just standard C++. There's nothing super fancy here, but you know, I'm just explaining what's going on. And then, so solver is just a string that the name of the parameter. Okay, so it will look inside T, find the parameter called solver, and then return it to you as a string. That's what it does. All right, so then suppose we discover that we want dice solver. We want to look at the parameters of dice method in particular. We extract a subtree called dice, and then, okay, so suppose we want to know the number of iterations. We again use the get method, except this time we want to extract an integer. And so the value that's stored under max iter inside that tree, the value is actually internally stored as a string. But we tell the params object how to interpret that value. So we're asking it to interpret it as an integer, and so return as an integer. All right, so that happens, and we write the value in this integer variable. And then, very similarly, the convergence criterion, except this time we want to interpret as a double. Again, so it's internally stored as a string. When you ask for this value, it extracts it as a string and then converts it to a double and returns it to you. That's how it works. Okay, of course, this is all assuming that the structure itself has been created elsewhere already. If right, so if say something is missing from that structure, you will get an exception that will say something like that key doesn't exist, which means that there's no such parameter in the param structure. Okay. Okay, let's move on. Now, suppose we have set up all the parameters. Now, how do we execute the methods? Well, as Anna said, we have a lot of different methods available, and we prefer not to have a single function or class that would know about all of them. For example, the old style CCMAN, old CCMAN's main routine had if statements everywhere because it had to check every parameter for every method to run it correctly. Now it's done differently in CCMAN 2, and here I'm showing what is done in this top level routine that's inside CCMAN 2.c file. Basically, what it does is it goes over every possible method that we have, and then simply checks the parameter structure whether the user has requested. So remember that params reader class already took the rem vector, interpreted as a param structure, and now the CCMAN 2.c, that class, takes the param structure and tries to run every possible method, actually executing those that are requested and skipping those that are not requested. So for our example, we will run CCSD, and then skip EOMEE, and then run EOMEE, run EOMEE-P, and skip the spin flip. Okay, that's how it works. So of course it knows about every method because it has to try to run every one of them, and that's fine because it doesn't know anything about the internal parameters of each method. So for example, it just knows that it needs to run the EOMEE, but it doesn't care about how this parameter structure is organized for that method. It doesn't need to check any of the parameters, just delegates that to the next level. Okay. All right, so that's all for the parameters class. I guess I'll just take the questions in the end. That would be the most reasonable. So if you have any questions about that section, please just type them in the thing, and I'll answer them later. Okay, so now how we deal with data objects, and here we're moving to something that's called context. Okay, so let's talk about this data structure called context. Context is an associative array. What is an associative array? Okay, so if you think about it as just a regular array, what is it? It's it's a sequence of objects of whatever type. Let's say numbers, right? So let's say integer numbers. You have something allocated in memory, like a slice of memory, where you have numbers one after another. That's a typical array. And well, you can think about it as a dense array, right? Because if you allocate numbers and then indices run from 1 to n, then they are located in memory consecutively from 1 to n, and every element does exist in that array, from 1 to n. Then an associative array is a kind of generalization of an array. So basically, it's a more abstract structure that simply maps a key to a value, right? So some key of some type, we use strings here, like shown on the slide, but in general, it can be anything, just some object that identifies something, and then value. And so the key is unique within an associative array, so there's only one. So each key exists only once in that array, and so an object is associated with that key. There's one unique object associated with that key. Right? So this is something that's called associative array. In reality, the underlying data structure is usually a map. So it's a kind of a sparse. So it's a sparse structure. Okay, so the context is simply then an associative array where keys, strings, identifiers are mapped onto some objects. And this is an example. Okay, I'll explain in a second how this, where this comes from. But I'll just show you an example of how a context is organized in a real calculation. In this particular example, it's a CCSD calculation. And so here in the left column are these keys. So the notation, so key is a general string. It can be anything, but the notation is hierarchical. So it's a logical kind of hierarchy, and it's very similar to a file system. So how we write a path to some file, and so we'll start with the roots and then put some directory, and then file name, right? And so, again, this is just a notation. This is just like an agreement of how we are going to do this. And okay, so we have this hierarchy fork subdirectory, if you will, where we have all these various objects, fork matrix, and then transformed MO integrals, hierarchy fork energy. And we'll have these objects all have different types. So the fork matrix is a 2-dimensional block tensor, and then the integrals are 4-dimensional block tensors. And then energy is just a simple number, real number. Then for MP2, we have MP2 amplitudes, T1 to 2, that are block tensors of the order 2 and 4 respectively. And then energies, just the correlation energy and the total energy, which are just numbers. And then under CCSD, we have amplitudes, energies, and, well, in this example, we also have density matrix. Okay, so we have 1 and 2 particle density matrices for the ground state. Okay, so this is the structure, or a structure that arises from some sort of CCSD calculation. Okay, so what you can see here is because it's hierarchical, you can isolate a subcontext from this total. For example, if you just wanted to pass MP2 objects without any relation to what higher level structure might be, you could just isolate this MP2 subtree and pass it to the recipient, and then the recipient will only see the MP2 objects under here. So a practical example where we might want that is, say, frozen natural orbitals, right? So that calculation consists of, first, a normal active space, like full space calculation of MP2, and then the second part is an integral transformation or orbital transformation, and then a full, say, CCSD or EOM calculation in this transformed space, right? And we can produce two different subtrees of for storing data, one for the normal MOs, and then a second one for the transformed frozen natural orbitals. They would have a similar internal structure, but we can have just one routine that does, well, for example, let's have a routine that does MP2. So we can pass either full MO or FNO context to it, and then the routine will be exactly the same. We'll be doing exactly the same thing, except perhaps unknowingly it will work on different types of orbitals. Okay, so that eliminates the dependency of these routines on what they're doing in the bigger you know, in the bigger logic of the program. Okay, and then let me show how to use the context. Again, the first line just shows that I'm here in this example. I'm using a vector from the standard library. This context GCTX comes from somewhere to us, and we create a context that's called CCSD from the context GCTX. So that's just going to be whatever GCTX is, and then it will append CCSD on the path, and so that will be our CCSD context. So the feature of the CCSD context is then it will not know the higher level structure. So it will know what comes from CCSD and down, but not what's up there. So it will only know, it will only have information that it needs to know. Okay, and then suppose we want to insert some piece of data into that context. We create a vector of integers called T1. Well, if this is a T1 amplitude for CCSD, it should probably be a vector of doubles, but let's just say it's a vector of integers for T1. We just create a new object using the new operator in C++. And then, so here we just populate the T1 somehow, we compute something, and then we want to insert that object into the context. Okay, so so we create a new item in this context. We'll call it T1, and then we'll create this funny object that's called resource counting pointer, and it's just something that we'll call smart pointers. I'll just explain in a second why we could do this. But so we create this smart pointer, pass T1 to it, and store that inside the context structure. All right. So what are the smart pointers, and why do we need them? It's a way of managing the lifetime of the object. Suppose you're computing CCSD, and you're creating a T2 object in CCSD, or T1, T2. You create them, but you want them to be used elsewhere. If you delete that object, so if you create in CCSD, if you follow the normal procedure where you create objects, you delete them there too. So if you delete T2, it's no longer available, right? So you create, if you end its lifetime inside CCSD, it's gone. You cannot reuse it inside EOM, for example. What do we do? We create a special pointer to that object, and it maintains the life. So the lifetime of that object goes on until we finally remove the last reference to the object. So once we no longer need it anywhere, and it's removed from every data structure, that special smart pointer deletes or frees the memory, right? That's just memory management trick. Okay, and so and then how do we extract objects from the context? So we take say the CCSD context. We want to extract that same vector T1, and so we use this funny function. Okay, so we use the function that's called get, and then it's a templated function. The template parameter is the type of the object, and then the label is T1. Okay, so we put it in a. So this function get is actually returns that smart pointer to the object. It doesn't return the object itself. So it returns this RC PTR type object we put in PT1. we can extract the reference, so the actual T1 object, by using the start operator, very similar to how we dereference normal pointers. Now, this T1 ref, this is reference to the object. It's exact same object as we created T1. It's not a copy. It's exact same object. Okay, so this reference T1 ref will point to the same object T1.
Now, when I write this on CPTR, this next to last line, so at this time, the count is object as copy in use, right? And if I want to tell that I do not need it any longer in this routine, so I need to do something with PT1, perhaps I delete or free or whatever.
Okay, so the question is, what happens to PT1? How do
I manage that?
Yeah. So okay, so internally in this context, CCSD, T1 is stored as RCPTR. And then RCPTR internally contains the actual physical pointer and the number of references to the object. And every time you make a copy of RCPTR, it increments number of references.
So
okay?
this operation.
So yes, essentially yes. So one copy will be inside the context, and so like up to here, that counter will be equal to 1. Okay. Once we do this again, we'll create another copy of that, another pointer to the object. It increments the number, so now it's 2. But when you say go out of scope, when the function ends, and that PT1 gets automatically deleted, because that's how. So this is essentially just another object, right? So the destructor is called by C++, and then that reference counter is decremented, so it becomes turned back to 1. Okay, but remember that we still have that object in the context. So even if we go out of scope, it is still there. It's not deleted until we actually destroy the context. Say if we no longer need it, and then only then memory is freed. Okay. 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 Let me go back for just a second. So if we look at this second to last line again, it looks kind of messy because we have it's a combination of last two lines, because if we want to get something from the context and then operate on it as an object, it's kind of I mean it's just you write this vector very verbose. You got a vector and 3 times here, and it's just not very convenient. Okay, so for convenience, there are introduced auxiliary objects, auxiliary classes. They're called loaders. So a loader is just a simple structure that's set up to get or pull specific data from the context. And then suppose we have some context GTX, and we want to pull all the Hartree-Fock data. So there's a class called HF loader, and as a see, it's constructed here. And then the constructor takes the context as a parameter, and then after it's constructed internally, it now contains things like Fock matrix and integrals. And of course, it doesn't contain the objects themselves, because we know that integrals can be big. It just contains the references. So it's a cheap operation to create a loader. So it just simply pulls the references from the context and spares you from writing those lines of code. Imagine if you had to write 2 lines of code for each of the integrals, and then you have 6, 2 electron integrals, and then 3 Fock matrices, and so on and so on. 2 lines of code for each, and then you have 1,000 lines in your source file. So yeah, so this is just a convenient way of doing that. Internally, it does that. It does this loading, but it's hidden from you. It just makes the code more readable.
You can write your own if you have new method, or you can use one that has, for example, more stuff than you need, because that would not be.
Well, so these are method specific. So for example, if we wanted to use CCSD loader to load CCD data, that wouldn't work. So the difference between CCD and CCSD is that in the amplitudes, we don't have doubles amplitudes in CCD, so we have just T2. And then in CCSD, we have both T1 and T2. If we use the CCSD loader, it will try to load both T1 and T2 from the context, and for CCD naturally there is no T1. Sorry, so when it tries to load T1, it will invoke an error. So yeah, they're method specific. In fact, I think in real code this is called CCSD T loader because it loads T part. It's just the T part. There's a separate say lambda loader that loads the lambda amplitude and intermediates the I loader. But okay, so this CCSD loader loads T amplitudes. Now again, the reason
simple containers that does not increase with an intermediate bit from context and actual code.
Right. So this is just to manage the complexity. Yes.
The simple container doesn't increase memory. Just
no. Yes. Yes. Yeah. So it's just to have all the CCSD data in one place and then address it in a nice way rather than try to pull all these objects. Because, well, so the context object, trying to pull the data from the context object is verbose, but it's not because I specifically did it that way, or like I tried to make it more complicated. No, it's just the reason for that is technical, because that's how C++ works, and then these were introduced to manage that complexity. All right, and so now you can see that we loaded HF, so Hartree-Fock objects and CCSD objects, and then here you say we want to compute the CCSD correlation energy, and so we can directly use those Fock matrices and amplitudes as simple tensors.
So simple structure which one can think of as just regular C structure that has stuff that you
exactly.
a bunch of stuff.
Yeah.
Only here we have a lot of flexibility because we don't put actual data, but pointers.
Right. Exactly. Yes. And so we can create 1,000 of these loaders, and there is no significant overhead related to that. Okay. All right. Okay. So let's finally go through an example. We're quickly running out of time here, but I'll just show you the code. I'm gonna show you some code that kind of snippets from simplified version. I'm going to go through the exact code that's you can find in source code, source files, and just basically explain what things do. Some of these things might be obvious, others maybe less so. But okay, the example is CCSD. The CCSD code is located inside CCMAN 2, and then all the couple cluster codes. So ground state codes are under CC. So in CC subdirectory, there's a file called ccsd.c. It contains the class that computes CCSD. Right. So this is CCSD top level function class. What it does is it takes when you construct this class, it takes two parameters, two arguments, the parameter structure and the context in which to run. So it takes parameters to basically specify or enable, disable some features, specify convergence criteria, and so on. And then the context is where data is read from and put back in. And then the run, this function that actually does the calculations, or like calls other modules. Its argument is the standard output stream, or basically where to write the output. Okay, so and then it begins by inspecting the parameter structure and seeing what kind of calculations to do or not to do. So remember that wherever the CCSD is called from does not know anything about this. So it doesn't know that CCSD consists of T, lambda, some intermediate density measures. It doesn't know anything of that. But this routine now is CCSD specific, so it needs to know whether we want to compute T's. PT is parenthesis T correction. Whether we want to compute some the intermediates, lambda amplitude, density matrices, properties, gradients, right? So, and then it just inspects the param structure and fills these booleans with what we want to do. And then we want to compute T. So the start timer and stop timer, you'll see them surrounding some calls. This is just to time each step of the calculation. Okay, so you if you compile Q-Chem with certain keywords, you can then output those timings to see, for benchmarking reasons or whatever. All right, so let's just ignore those for now. But the essential part here is that it calls CCSD_T, and that's a similar module, and that's the one I'll show you later. It's that one computes T amplitudes. Okay, so it's T amplitude specific, and again, it passes context and okay. Notice this structure. So MGCTX, the context that was passed to us from whatever called the CCSD function, CCSD class, and then MPAR is the parameter structure. Okay, so it passes. It takes. So MPAR now is at the CCSD. So the root of the MPAR is CCSD. Okay. Now we only want to pass the part that pertaining to T. Okay. So we extract that subtree T, and so the CCSD T doesn't even know that it's called from CCSD. So it's given these parameters. We can create some other funny method that uses, it's completely different, but for some reason it uses the same solver as CCSD for T amplitudes, right? So and we can create a very similar structure and then completely reuse that solver, right? So call out of the CCSD, not call out of the CCSD model, but something else. Okay. So as long as we recreate that proper structure of parameters, it's all fine. All right, and then okay. Let's look at this line again. So what this does here is that CCSD_T is the name of a class. So it creates, it constructs an object, and then .run is just simply runs this run method, calls the run method on that newly created object.
And MGTX, it's a context that is local for this class that was initiated in the constructors.
Yeah, exactly.
So each constructor, you take whatever context was passed, and then that's your starting point to pass it to the subjects.
Right. Yeah. So because CCSD T. So this GTX was passed to CCSD from somewhere, and then it simply passes this context on to T, and we'll see it in lambda. Yeah. And then this context, there are two purposes for it. One is to read the input and then put the output in the same context. All right. And so so then this run function is called, and then once because this is a so-called anonymous object, we didn't give it a name. There's no variable name associated with this object. It's simply destroyed right after we call this run. Okay, so this is basically this is a concept that's called a functor. So it looks like we're calling a function, but we create an object, initialize with some parameters, and call a function with something that's called a functor. Okay, so then we've computed T. If parenthesis T energy correction is requested, we call very similarly the CCSD_PT, and then after this we have computed all the CCSD energies, so we can print. So this print summary function, I'm not showing the function itself, but basically what it does is prints the CCSD energy equals and then CCSD parenthesis T energy is this and this and so on.
So it's also
then T amplitudes. Yeah, right. So this is just a member function. Yeah, we don't care much about it right now. So yeah, this return statement is basically it's just this function returns true or false. Returns false if say T didn't converge, and so then if T doesn't converge, it actually prints that T did not converge. So it just returns. So prevents other calculations from running. All right, and then L for lambda amplitudes. Actually, I think I'm missing here. Yeah, I'm missing one part here, which is I's, so intermediates. So we compute T, then we compute some intermediate intermediate tensors, the I tensors, and then lambda depends on those I's. But yeah, so this is very similar part that computes intermediate. So we call for lambdas, then density matrices, all the same idea, right? Density matrices. Okay, this is a curious one. All right, so here we pass two contexts. One will create our so GCTX is the context of this whole calculation. So it contains the Hartree-Fock data, MP2 data, CCSD data. Now we want to compute a density matrix, but this CCSD DM is designed so that it loads essentially we want to specify where to put the density matrix. So the path where to put density matrix is not fixed as in other places, but it can be flexible. So the input context would be, so it would read the input data from this GCTX, but it would put the density matrices themselves into this DM-CTX. Okay, so on the path would be just CCSD DM, and then it would create matrices called G1 and G2 and put them in DM-CTX.
So, no, I don't understand the difference. Because when you have T, then you compute T and you put them in CCSD/T.
Yes. Yes. If we compute T, we put them in CCSD/T. Well, so in this particular example, actually, it's not very. Let's see if it's useful. Well, yes. So in this particular example, it's not very useful to do it this way. It's actually very useful in EOM, where we can isolate a certain state, because the density matrix procedure is the same for every state. We take the context of one state, put in one DM, and for second state, put in a different DM, third state, different DM. It's just the same idea here. Sometimes we want to have different outputs, where to put the output, different place. So that's why it's you can pass it this way. Let's see. And so, okay, so let's go through this properties example. So the properties is for CCSD, the input is the density matrix and energy, and the output is some properties, let's say mu, the dipole moment. Okay. And what it takes here is the global context of the calculation. Then state CTX. So this is a context of the state. In our case, it's the ground state CCSD. The only piece of data it needs from that state is the energy. And then the context of the density matrix. So this is state-specific density matrix. And then parameters that regulate how to compute the properties, like which properties, for example, are enabled, which properties the user asked for. And then prop CTX is the context where it puts the results. So it computes mu, it puts the value of mu in the prop CTX.
So when I run specific function run for different, I can run it just such that it uses context which is specified for this calculation, the some GTX which I set upon constructor of the class. Or I can create a new context and write a function such that it uses different context for all.
Yes, yes. So yes, you can, you can put any other context. Like going back to say when we have two different molecular MO spaces, like we have a regular Hartree-Fock MOs, or we can have some, let's say, frozen natural orbitals, so just different set of MOs. The structure of the contexts is the same. They're two different contexts. Because say the integrals, all the objects will be different, but the structure of them will be the same. And so we can call CCSD once with the normal orbitals, and then the second time exact same class, well, exact same procedure, but just run on a different data, different set of data. Okay. And then finally, let's go through, just quickly go through the T. So this is CCSD_T. This is a piece that computes T amplitude. So T amplitude is an iterative procedure. We start with an MP2 guess, and then do dice for convergence, and then do some iterations and come up with the converged resulting T amplitudes. It starts, so this is again, it's the class is organized as a functor, so it's initialized with the context and the parameters, and this is a run function member, and its argument is required to print the output, okay, so the stream where to put the output. It starts by reading the solver, and if the solver is not dice, it simply bails out because the only one implemented right now is dice. Then it reads some dice parameters. And yeah, by the way, so this code is directly taken from the repository. So this is what you see in the source file. It isolates the dice parameters in a separate subtree and tries to load. So start at which iteration to start dice, the number of vectors in the subspace, the number of iterations, maximum number of iterations, then two convergence criteria. So that's the dice parameters. Okay, and then it reads data. It actually says set up the context, but really what this means is load the data from the context. And so it loads the active spaces, the active space. This space, it will be basically S, this object will contain O and V, so the properly prepared space objects for occupied and virtual spaces. Okay, and then there are various combinations like OO, OV, VV, OO, VV, and so on. So these are already prepared for you, so you can create tensors in those spaces. Okay, again for convenience. And then HF loader, as I showed earlier, is it just loads arbitrary Fock data, Fock matrix, and integrals. MP2 loader loads MP2 amplitudes, MP2 energy, and all the MP2 stuff. And then we create a new context. Well, what do you mean create? So we take this context that was given to us by whoever called this CCSD_T, and we just simply create a subdirectory called CCSD. This is where we will put the results, right? So create the CCSD subdirectory. We'll put our T amplitudes there. So this thing is called CCSD here.
So where would this is a little bit unclear for me. Where is the right place to create this context and how to know where it was created? Was it created? Because I would think that if I call CCSD solver for T amplitudes, the CCSD context already.
Oh, okay. Okay. So the question is where to create. So where to create the context, and so this is not really creation of the context as you might think. It's it's simply a pointer, right? So it points to where to put. So think about it this way. In fact, that's how it works. So we have if you think about the context of subdirectory, we have this absolute path to this directory, right? So it's there's this directory 1, 2, and the whole hierarchy. So absolute path. But then there's a pointer pointing at the current subdirectory where we are, right? So 1, 2, 3, whatever the path is. So there's this whole part of the path that's not visible to us. So it points out where we are in the global structure, and then we, whenever we ask something from this context, ask for whatever object piece of data, then it starts. This is just the path from the current directory and on. Okay, but whatever precedes it is hidden. Now, when we create this context object and then say that it's created from this MCTX, it simply moves us to the CCSD directory. So it's like we're somewhere in some directory, and then we do CD CCSD, and now we're suddenly in that CCSD directory. And whenever we have a file name from there, it's related to the current where we are. It just simply establishes our position where we are in this hierarchy.
Yeah, but I can create this CCSD starting from different ports, right? And,
right.
put different stuff in it, and I'm a little bit confused why, for example, because that's not the first thing to be run in CCSD calculation, right? When I go to CCSD calculation, that's the kind of main material showing physics.
Yeah.
Well, it's close to the first one. So I would think I should create this context CCSD just the first time I enter into CCSD class and go through this.
Oh, but you see, oh, I see what you mean. I see what you mean. So you think that we should create the CCSD context up there and then simply pass this as to where to put the output. That's a good point. In fact, I agree with you that it should be done that way, yes. Yeah. So to complete the logic, I think the reason it was done this way is just, it was done like that in the beginning and then never had time to. But yes, I agree with you that logically the correct way to is then to just pass that to CSD context. Yes. Okay. This way works too. So then in CCSD-T we create MP2 amplitudes. So CCSD ampl is just some structure that contains the CSD amplitudes. Make MP2 guess is just a member function that takes MP2 amplitudes, MP2 T's, and puts them in this guess structure. This makes a copy. And then this is a few lines about how to set up the solver. So I guess I'm not going to explain in detail how this works. It's a separate, I guess it's the topic of a separate seminar. How this is setting up the libsolve to solve the dice for CCSD amplitudes. But this is what it does. Simply sets up the solver. Then finally, the last line here is just runs the solver. So that's where when it calls run, that's when iterations start, and then you see those energies printed out on the screen. So the output file. Let's see. Okay, and then finally I'll show you how, once the amplitudes are solved for, how we save them in the context. There's a member function called save dice results that takes the resulting T amplitudes, the converts T amplitudes, and puts them in the context. It creates these smart pointers with the objects. In particular, the objects that it puts in the context are the energy. So this just.
They are now called different, not
yeah. So auto PTR is just a wrapper around simple pointer. Just you can think about it as just a simple pointer. Yeah. So it's simply it's like a scope pointer. So when you create an object in this scope, so in this function, once you go out of scope, it's automatically deleted. So you can see that you do new here, but even if we close the function here, so even if we returned here and didn't go all the way to like saving that in the context, if we return from the function right at this point, then those objects will be automatically deleted by auto PTR because the scope is ended. So once you go out of scope, so you call new, but you don't call explicitly delete. But when auto PTR is destroyed, it calls delete. So this is just a kind of safe way of dealing with say.
So in principle, this doubles automatically to buzzer, of course. But if I have arrays, that says we possibly delete this.
Yeah, sure. Yeah. Well, no, it's different. It's funny with arrays because auto PTR does not support arrays. Arrays need to be.
Why do you need it for doubles? Because doubles will be destroyed anyway.
Well, it's not just a double. We create a new double. We create double on the heap. So,
no,
like
if I write in this line, say double energy, I will create a double.
Oh yeah. So the reason is to put this piece in the context. It has to be in the form of a pointer. Not so. If you just put double, if you write double energy equal that energy will be created on the stack. Yeah, we need to create it.
And then the pointer will not be freed unless I do free.
Say that again.
Well, if I create the pointer to double and new it, then I can put the stack in the context, but then I will have to at least delete this pointer before I enter the scope, because otherwise it will not be free.
Well, okay, so if you put it in the context, it saves, it wraps that pointer into this resource counting smart pointer. So
No, it doesn't create the code.
you don't yeah, so you don't actually need to delete it.
Okay.
This is done here just for simple safety. That I guess it's kind of overthinking it a little bit. But say if something happens here and then you get an exception, and that happens between you save, so between you create these objects and then save them in the context. Say if one of these two created, or this function creates an exception. Exceptions in C++ are handled such that you simply this function doesn't continue; it just jumps out of it, and you don't even know it. So you would have these objects created, but you would never delete them. If you just had, say, energy equals new double, then say T1 equals new Libtensor or whatever. Then if it, because of an exception, it returned from this function, then you would still have memory leaks and have those objects created. If they're wrapped into this auto PTR, then it's all done properly. So if you have an exception, then the C++ has a special way of cleaning these things up.
And this type is called out of PTR, but I work with this as if it is double. It's more like a reference.
It's like a pointer. Yeah, you work with this as a double star.
Okay,
Yeah, it's like a double star.
Okay,
Yeah.
So it's just like regular code.
Yeah, exactly. So for example, see here I passed T1. If T1 were just a simple pointer. Yeah, so this is outer pointer. Yeah. Oh yeah, so yeah, so those are pointers. Those are actual pointers there. Yeah. All right. So then okay, so we prepared all these objects to put in the context, compute the CCSD energy. So energy here is a pointer, so we use this dereferencing mechanism to tell compute function where to put the energy, compute the total energy. Now we call this set immutable. So block tensors this is for Libtensor. So block tensors have a way of kind of freezing the contents of the tensor, and basically saying that you may no longer modify the data in the tensor. And if you try to, then it will not let you do that. So we simply say that, okay, we've computed T1 and T2, and we're just saying, okay, we don't want it to be changed anymore. So we set it as mutable objects. Okay, and then we simply use the insert function to put data in the context. So
what is essential here is that when I put it into context, I use create the source count point, and then I put that.
Right. Yes.
So,
yes.
Then, so in principle, I could have just taken this amplitude T1 and put it directly there.
Yes, you could do that. Yes.
Yeah, so that would work, but this way you have memory mixing in case of exceptions. But in principle, other than that, it would work.
Right. Yes.
Yeah, I also have a question. So basically, when you do this insert using this RC pointer, are you using the same, like basically, are you just using the same pointer to the memory, or you just create a new, like allocate new memory and copy it from energy? Because you used after pointer here, so when you go out of scope, after pointer should delete your memory, right?
Right. So it's the same memory, and the RC pointer internally is written. There's a trick, so it extracts that pointer from it, takes it away from the outer pointer, and tells it not to delete it anymore, and then use it. But so it does not allocate memory again. It's exact same object. Yeah. Okay. More questions? Okay. I hope. Yeah. I just go R. Good question. Okay, so this is just it's not related to the context itself, but it's related to how things work in the Libtensor library. And then we have let's see. So Btensor in Libtensor is class that implements this Vtensor I interface. And although we use, so there are template parameters, both of them, interface and the class are templated. First parameter is the dimensionality of the tensor, and the second is the data type. Vtensor in reality has a third parameter that's default, and it's the allocator which to use to allocate memory. Basically, we're just hiding that information. So by going from Vtensor to Vtensor I, which is simply removing a piece of information that could prevent us from being able to read that back, just technicality in a way.
What is hierarchically? So Vtensor I does not have class?
Yeah, so Vtensor I is just abstract-based class.
So you just said that, okay, this class is this properties and attributes, and you don't know what they are.
Exactly, yeah. So by doing this, we're hiding, and then Vtensor is a real...
You can write your functions that take Vtensor because Vtensor I because now objects are Vtensor. Right?
Yes.
And then you find Vtensor, you define some special functions.
Yeah, exactly. Yeah. Okay, finally done with the code. Last slide. I'll just give you a brief instruction how to start working a new method. And then, so the first thing to do is identify prerequisites and results. So essentially, you need to think about what kind of calculations need to be done prior to this new method, whatever that is, so that those results can be reused. And what kind of data that method is producing. It's, I mean, it's very abstract instruction, but there is nothing less general to say because I don't know what kind of method you're working on. But yeah, essentially you need to see whether, suppose your method is, well, okay, let's say something in particular. Let's say you have a new type of perturbation theory correction to CCSD energy, right? That's not yet implemented. That uses T amplitudes. So you know that you need to have converged CCSD amplitudes before computing your correction. And so that's going to be the prerequisite. And then you need to make sure in some place to make sure that CCSD is computed before your function is called. So then when that correction is called, you already have the data computed and you can access it. Okay, then the second step of the procedure is to essentially implement the new method as a class and then look at existing methods. Maybe the new method is very similar, or not very similar, but maybe conceptually similar to something that already exists. Say we have things like just energy correction type, which is, for example, CCSD parentheses T, or an iterative method, which can be any CC method, is an iterative method. Excited state method, you can take any EOM method and take it as a template for any sort of excited method, and so on. So, yeah, so it's very likely that an existing method will be a good template. Then, because you've created a new method, created a new class, you need to add it to the CMake lists.txt to make sure it compiles, including the compilation procedure, and then open params reader, and there add a section that will set up the parameters for your class for a new method. And well, it has to set up the parameters for the class and make sure that the prerequisites are enabled. So if your method requires CCSD to be computed, then in there, like if you take a look at how EOM is set up, you'll see that it looks at it sets up EOM, all the EOM parameters, but then also makes sure that CCSD T amplitudes are also called, so enabled. And then finally, in the main routine CCMAN2.c, just add a call to the new method, and then it will be actually called if it's enabled in the param structure, or not called if it's if the user did not request it. All right, that's all. I think this is my last slide. It's very simple. five basic steps, and you're done. Okay, so I know that it took much longer than it was supposed to take, but yeah. Okay, thank you for listening, and Dima, you can.
Thank you very much, Женя. Okay, so please, if anybody has any question to Zhenya or Anna, please write them here in the questions section.
No questions. No listeners either.
No, we're actually listening still. Well, still the 3 listeners. Still 3 attendees. It looks like no questions. No?
Do we have questions from here? So I have a question like in the params reader, right? That's basically would be a place where all the complexity is handled in terms of prerequisites, and there you can nothing up, right? If you change prerequisites to run some calculations, potentially maybe incompatible with some other calculations, right? So and that's a place probably where some parameters should be checked for compatibility, right?
Yes, that's.
So that's.
Well, there's a few things that I did not mention, but I probably should, because right now params reader is also a graveyard of all different options. However, the internal structure is different. So they're all in one file, but it's very easy, or we might as well just split it in different files, because internally it's very well separated. And, we can then take a piece that's related to CCSD and move it to CCSD part, and then EOM to EOM and so on.
But it's still, there should be place to run something very cheap. Just like writing these functions, just parameters where some certain combinations will be checked and parameters will be set up to do this correctly.
Well, yeah. So when you inside params reader, if you go and look into it, yeah, you'll see some pieces where it will check if it sees that there are incompatibilities. Well, let's see. Let's take an example. Well, what comes to mind is, say, EOM. There are different ways to request EOM. There is EOM, say, EOMEE states keyword, and then EOMEE singlets and triplets. But singlets and triplets are not valid if you have a closed shell restricted reference. So if you try to use an unrestricted reference or a row-href reference, and so open shell reference, and use singlets of triplets, it will say that, oh, you cannot use this keyword, you have to use keyword states. And then EOM returns you a mixture of whatever multiplicities these states end up being. Yeah, so params reader is responsible for making sure that the input parameters are the same.
Now, do we delete stuff from the context? Because
there is a technical possibility to do that, but normally you would not want to do that.
Because
you don't know when, like that.
No, that's the question, and in principle, you don't want to start the development because they're limited with resources. And if I computed something big, like let's say intermediates for EOM, right? Then I do EOM calculation. Then after EOM calculations, let's say I do not need my intermediates anymore, but I want to do something else. Like calculate maybe response properties and other things. Then, in principle, I may want to delete big intermediates and keep only what I need. So it does complicate the execution for you because you do not know when to finish them, right? But that's something that would not be well. Maybe before parentheses key. Well, before parentheses there is not much stored, but
well, okay, so there is no general solution to this because it's well, it's nearly impossible to predict whether the data will be needed further down the road.
But what would be the right way to at least find out, what is in the context, and let's say I'm programming something new, right? I kind of have that idea where I should stick my new method, right? And I kind of want to know what would be the context at this point, what is likely to be, and where it was put in and where it was deleted, if it was deleted. So how do I figure this out?
Well, so in principle, if we wanted to do that, we could introduce special task that would be cleanup. So it wouldn't do any calculation, but we would just take the context and then delete things from it. And say we can invoke those after we know for sure we no longer need that piece of information. Although, in reality, there hasn't been a situation where we need that kind of.
Because we use device computers.
No, but it's just so far our flow is such that we accumulate data and we use it all, and then we stop and then we just remove all of it after we're done. So, but if that kind of cleanup is needed, in principle it's possible to do. Yeah.
So somewhere like the CCMAN 2C, right? If you have basic picture, we can call something like that cleanup in between different classes, right?
Yeah, like for example, we wanted to remove. Suppose let's consider. Yeah, sure. Okay, let's say we wanted to remove these CCSD intermediates. So we compute CCSD-T, CCSD intermediates, and then do a bunch of EOM stuff. And let's suppose we do, I don't know, something else after EOM, but we know that we no longer need the intermediates. So yeah, we could insert something like cleanup CCSD and have CCMAN, the main routine CCMAN to call it after EOM to clean up CCSD. And yeah, so that's possible. But again, in practice, we never needed it so far. But yeah, if we do need it at some point, yeah, let's do it.
Okay. So I guess no other questions.
So then, yeah, let's say bye to our
Okay.
guests.
Yeah. Thank you very much for attendance. Yeah. So we.
We don't have this on YouTube.
Yeah, we recorded it, so it will be on YouTube shortly.
PDFs you can also put them on YouTube.
Sure. Yes, sure.